You know, in physics, we build our understanding on a set of foundational rules. But what happens if one of those rules isn't a law of nature, but just a choice we made for convenience? Today, we're going to pull on that one thread in electromagnetism and see if it unravels to reveal something much, much deeper.
Right, so if you've ever taken a physics class, this probably sounds pretty familiar. You're taught that the vector potential, this thing called A, is just a mathematical tool. It's like scaffolding. You use it to figure out the magnetic field, and then, once the job's done, you're supposed to just kick it away.
But what if that scaffolding isn't just scaffolding? What if it's actually a load-bearing beam holding up a part of the building we've never even seen? That's the huge question we're digging into. We're going to explore a theory that says this auxiliary function isn't auxiliary at all. It's the star of the show.
So here's our game plan. We'll start with that one big assumption everyone just takes for granted. Then, we'll see how questioning it reveals a hidden type of magnetic field. From there, we'll rewrite the core equations of electrodynamics, which, and this is wild, predicts a whole new kind of light. And finally, we'll ask, is there any real-world evidence for any of this?
Okay, let's dive right in with that convenient fiction. It all boils down to how we define, and more importantly, how we constrain the vector potential.
So in the standard model, the vector potential A is kind of like a behind-the-scenes assistant. Its only job is to help you calculate the real star of the show, the magnetic field B. Once B is on stage, A is supposed to disappear back into the wings.
Now, to make all the math work out cleanly, physicists apply this rule, a gauge condition, that says the divergence of A has to be zero. Think of it like a plumbing rule for the universe. It forces the vector potential to always flow in perfect closed loops. No sources, no drains, no leaks. It's a really tidy choice for doing calculations, but is it a physical law? The theory we're exploring today says, probably not.
So, what happens when we start to poke at that plumbing rule? Well, this is where we see the first cracks appear in the standard picture. We're going to step out of the perfect textbook world and into reality by looking at a simple piece of wire. See, in the idealized world of an infinitely long wire, that div A equals 0 condition works just fine. But really, when have you ever seen an infinitely long wire? In the real world, we have antennas, circuits, finite things. And when you actually do the math for a real finite piece of wire, something incredible happens. Its divergence is not 0. And that changes everything. Because if the divergence of A isn't 0, it has to be equal to something. This theory proposes that this something is a totally new kind of magnetic field, a scalar magnetic field. Unlike the magnetic field you're used to, which just curls around in loops, this one acts a lot more like an electric field, radiating outwards from sources and flowing inwards towards drains.
So the idea is that the vector potential isn't just one thing, it's made of two parts. Field theory tells us you can break any vector field down into a rotational or vortical part, think of a swirling whirlpool, and a divergent or potential part, think of a fountain. Standard physics only really acknowledges the whirlpool, which gives us the normal magnetic field. This new theory says, hey, that fountain is real too, and it's the source of this new scalar magnetic field.
And this new field isn't just some interesting little quirk. It's the key to a whole new vision of electrodynamics. By accepting that the vector potential is more than just a trick, we have to go back and rethink the most fundamental equations we have.
In full-blown electrodynamics, that simple div A equals 0 rule gets an upgrade to something called the Lorentz gauge. It's more sophisticated, yeah, but it's the same basic idea. And just like before, standard theory just sets this entire expression to 0. Gone. Why? For mathematical convenience. It's a calibration, not a law of nature.
And this right here is the absolute heart of the argument. Instead of just forcing those terms to equal 0 because it makes the math easier, this theory asks a profound question. What if they equal something real? What if this mathematical shortcut is actually hiding a physical law?
And boom, here it is. This is the crucial leap. The theory takes the exact terms from the Lorentz gauge, the ones we used to just throw away, and says they physically define the scalar magnetic field H star. That mathematical constraint is transformed into a physical law. The mathematical trick becomes a statement about reality.
The result is frankly beautiful. On the left, Maxwell's classic equations. On the right, the generalized system. And you can see these new terms just pop into existence. The gradient of our new scalar field, H star, acts as a new source for the regular magnetic field. And the change in that scalar magnetic field over time acts as a new source for the electric field. It's a more symmetric, more complete picture.
When you follow the math, these new equations predict a much richer electromagnetic reality. Not just one magnetic and one electric field, but two of each, a rotational and a divergent component for both. This symmetry is really profound, and it leads to one heck of a startling prediction.
Right. This new symmetry isn't just pretty math on a page, it predicts an entirely new type of electromagnetic wave, a second kind of light that's been talked about but never really accepted into the mainstream.
We're all used to light being a wave that wiggles up and down as it zooms forward. But just like sound waves push and pull the air in the direction they're traveling, this theory says electromagnetic waves can do that too. They can be longitudinal. And that is a radical idea.
Here's the difference. The waves we know, light, radio waves, they're transverse. Think of a snake slithering side to side while moving forward. The wiggles are at a right angle to its direction. That's our E and H fields. But these new E waves would be longitudinal. Think of an earthworm, inching along. The bunching and stretching happens along the direction of travel. That's what the electric field would be doing.
Okay, so this is some pretty mind-bending theory. But is there any evidence for it? Are there any weird phenomena out there that the standard model has a tough time explaining, where maybe this new idea fits? Some researchers certainly think so. There were experiments by Monstein and Wesley that seemed to show energy transfer that shouldn't be possible with normal waves. Others claim to have actually turned laser light into these longitudinal waves. And what's really fascinating is that the idea of longitudinal waves first popped up in quantum electrodynamics way back in the 1930s.
But, and this is a huge but, as this quote points out, to make the new quantum theory play nice with Maxwell's older classical theory, these longitudinal waves were just defined out of existence. They were labeled non-physical and swept under the rug to preserve the old paradigm. It was a choice, not a discovery.
And that leaves us with this massive, tantalizing question. What if they made the wrong choice? If this scalar magnetic field and these longitudinal waves are real, what could they unlock? Could they lead to new forms of communication? New energy technologies? Could they help us solve some of the deepest mysteries in the quantum world? And it all started by questioning one simple assumption and asking if a helpful mathematical tool was actually a fundamental part of reality all along.